In order to do roof framing calculations, we will first review construction geometry with triangles and a little bit of trigonometry. The isosceles triangle is a triangle that has two sides that are equal. And if you were to bisect an isosceles triangle right down the center, then what you would have would be two right-angled triangles. And all of our roof work is going to be focused on right-angled triangles, also with the two sides being equal. We have the isosceles triangle with a perpendicular bisector, but there are some other things that we know as a result of this. Perpendicular bisector divides the isosceles triangle into two congruent triangles. And when triangles are congruent, then all the sides and all the angles are equal. This is important for roof geometry, especially the gable roof. If you were to take a cut through a gable roof and then look at the side view, you would actually see an isosceles triangle. The sloping sides of the triangle would be the slopes of the roof, and both slopes are the same angle, and so therefore the angles at the base are the same. So all the parts are going to be exactly the same. So when we look at a roof, we're only going to deal with half of the triangle in order to calculate the common rafter. A quick review of the Pythagorean theorem will show us what we need to know for roof geometry. Remember, Pythagoras only works for a right-angle triangle, so there has to be 90 degrees. In this triangle, the vertical arm A, the horizontal arm is B, and the hypotenuse, which is the sloping arm, is C. And A squared plus B squared is equal to C squared. Now what that really means is that if we were to put a square with sides equal in length to A and another square with sides equal to length B, that those two areas together would be equal to the area of the square that we would put on side C. There's a short video link here that you can see how this graphically is put together, and it'll really sink into your head when you see how it works. So with A squared plus B squared equals C squared, then C will then be equal to the square root of A squared plus B squared. And that's what we're going to do, because C in roof geometry will represent the rafter. For doing our work in roof geometry and for the rest of our calculations that we have to do in carpentry, I would recommend that you get a DAL calculator. This picture here is one of a Sharp calculator. DAL stands for Direct Algebraic Logic. You're probably looking at about $15 for something like this. The good thing about a DAL calculator is that you write your numbers, you enter your numbers and your symbols just as the way you would write it on the page. And so if we're looking at a right-angled triangle, and we're going to use Pythagoras' theorem, if we're given that the A arm is 4 feet, the B arm is 3 feet, and we had to find the sloping sides, we know that C is the square root of A squared plus B squared. So on the calculator, on a DAL calculator, you would press the square root button, then press open brackets, then 4, then press x squared, plus, then 3, then x squared, then you close the bracket, and then you hit equal. And what will appear on the screen of your calculator will be the square root of 4 squared plus 3 equals 5. This is a diagram of a gable roof. You can see the span measuring from outside to outside, from exterior wall to exterior wall. The run being half the span, the rise being the vertical distance that the roof will rise over the run, and then the diagonal that goes across the two would be the hypotenuse of the right triangle, and that is the length of the common rafter. So we have run, rise, and common rafter length. So that's our right angle triangle. So here we have the roof triangle with the same numbers on it and the same letters on it: total run, total rise, total span, and length. At the top would be the ridge. So now we're treating the rafters as though they're just lines. So there's no dimension to them, no thickness. And up in the top right hand corner you have the unit roof triangle. So the unit roof triangle, now it's turned upside down in this picture. Architects generally turn them upside down so they fit neatly on the page. If we were to flip it the other way over, we would see, of course, that it's similar to the roof triangle. The unit triangle has a unit run on the bottom, a unit rise on the side, and then going across on the slope would be the unit length. This is called the slope triangle, and this is actually the same that you learned in high school, that slope is equal to rise over run. So if you remember doing graphs, the slope was denoted by the letter m, y equals mx plus b, if you can remember that. The slope was rise over run, and that's the ruse. Slope is equal to rise over run. And so what we're going to do is use the principles of similar triangles and ratio to calculate the full length of our rafter. Here we have two similar triangles, or two triangles that are similar to each other. They both have the same angle, or actually they both have all three angles the same. Both of them are 90-degree triangles, and the angle down at the bottom is equal on both of them, and the angle at the top are the same. So the roof slope triangle, this is denoted either as 7 in 12, 7 over 12, or 7 to 12. And 12 is always the unit run. And that's because, of course, we're in the imperial system. 12 inches equals 1 foot. So everything is rated over a foot. So this particular roof slope is going to be a 7/12 slope. And you can do Pythagoras on this to figure out the hypotenuse, and the hypotenuse is 13.89. On the big triangle now, which represents the entire roof, we know that the run of the building is 18 feet, which would then mean that the span of the building is 36 feet. So by similar triangles, we can actually say then the total rise, which is we're going to denote by x, the total rise, the ratio of the total rise to the total run is going to be equal to the ratio of the unit rise to the unit run. And this is denoted by x over 18 is equal to 7 over 12. Now we multiply both sides by 18. On the left-hand side we get just x, because the 18's cancel out. And on the right-hand side we get 7 times 18 over 12. Running the numbers through the calculator, that becomes 10.5 feet. So the total rise for this roof is going to be 10.5 feet, or 10 foot 6 inches. Now there's two ways we can figure out the line length of the common rafter, which is the slope, where the rafter will go, right? So one way is our triangles. We can say the ratio of the line length of the common rafter to the total run, which is 18, is the same as the ratio of the unit common rafter, 13.89, to 12, which is the unit run. So again, LLCR over 18 is equal to 13.89 over 12. So now we multiply both sides by 18, and we find that the line length of the common rafter is 13.89 times 18 over 12, which is 20.835 feet. Or we could use Pythagoras, because now that we know the sides of the full triangle, the total triangle, we know the base is 18, and we know the rise is 10.5. We can then take the square root of 10.5 squared plus 18 squared. And that will give us 20.839 feet. Now notice there's a little discrepancy here because of rounding off decimal places, 13.89 decimal places. But when we convert this now to feet and inches, we'll see that the difference is negligible. And the total line length then of the common rafter is going to be 20 feet, 10 and a 16th inches. If we were to use the similar triangle number, we would simply get 10 and a 32nd inches, so it's negligible. Here we have another triangle representing a gable roof. The span of the building is 28 feet, the run of the building is 14 feet. We know that we're given that the slope is 9 and 12, which is given by the unit triangle. And from that, we're going to calculate our total rise and the line length of the common rafter. So first, we do similar triangles. Total rise to total run, x over 14, is equal to unit rise over unit run, 9 over 12. And solving that, we get then that x is equal to 10.5. So now that we know the big roof triangle, We know the base, and we know the run, and we know the rise. Now we can calculate the line length of the common rafter. So again, like I said, we could do that by Pythagoras, or we could do it by similar triangles. And notice the way I set up the similar triangles this time is slightly different to the way I did it last time. And this works always as long as we make sure that we compare apples to apples. So in other words, now I'm going to compare the line length of the common rafter and the roof to the hypotenuse of the unit triangle. So I'm going to go LLCR over 15, and then I'm going to compare that to the two runs. But I have to make sure I'm going the right way. So I go with the run from the big triangle to the run of the small triangle. So LLCR over 15 will be equal to 14 over 12. Notice I've dropped the units because they cancel each other out. 14 feet over 12 feet is the 14 over 12. So then we get LLCR is equal to 14 times 15 divided by 12. That will give us 17.5 feet or 17 foot 6. Now when we compare the line triangle with an actual roof, we'll see that there's some differences. The angle still looks the same, but we'll see now that the hypotenuse that ran from the outside of the exterior wall isn't quite exactly in line with the top of the rafter or the bottom of the rafter. So the rafter sits on top of the wall with a little notch cut out of it, and that's called the bird's mouth, so that it can be secured and fastened to the wall. And we notice that there is some amount of wood above and some below it, so it's not quite exactly the same. But we can see how it works out because we have the same line, and we can see the parts of the roof and the parts of the rafter. So there's a tail cut to the rafter, there's the body of the rafter, and up at the top there's a plumb cut where it fastens to the ridge board. Then you can see a collar tie which will hold opposing rafters together, and then the ceiling joist will also hold the rafters together, and at the same time it will hold the exterior walls and keep them plumb. In this picture what we have is two rafters sitting on a building, so we're seeing the exterior walls, two rafters, and they meet up at a ridge board. In the dotted line what we have is the actual roof triangle diagram that we looked at before. So you can see that the rafter is sloping on the same angle as the line length of the common rafter, same angle, no difference, no slight shift, it's exactly the same angle, but you will see that the actual top of the ridge board is higher than the total rise. So those are two important things to keep in mind. The other thing you'll see here is that the actual length of the rafter after we've cut it is going to be a little less than the line length of the rafter that we calculated, and that amount less is going to be determined by how thick the ridge board is, and it's going to be half the thickness of the ridge board. So if in this case we have a 2x8 for the ridge board, 2x8 is actually 1.5 inches by 7 1/4, so half of 1.5 inches is going to be 3/4 of an inch. On the bottom end of the rafter we have the tail that hangs out. You can see the dimension referred to as projection. Projection is measured on the horizontal. The same distance on the slope is called the overhang, and quite often people mix these terms up. A lot of times they say roof overhang when they really mean roof projection. Now note that if on a set of plans you're given that the roof has a 16-inch projection, that includes the rough fascia, which is usually 1.5 inches thick. So you have to be careful then when you're cutting your rafter that you cut your rafter so the tail of the rafter has a 14.5-inch projection as opposed to a 16-inch projection. That way, once the fascias are nailed on, then we're going to have what we've been asked to build. One other dimension to look at is the rafter span, which is denoted by the blue line on the right-hand side. And the rafter stand, sometimes referred to as the height above the plate or the hap, it's dependent on the rafter size. So whether the rafter is a 2x4, which will give a certain amount of wood left vertically above the bird's mouth, or a 2x6 or a 2x8. And that will change depending, of course. So what will happen is that the ridge board will actually be higher depending on the depth of the rafter itself. So if we have a 2x4 rafter, the ridge board will set at a certain height. But if we have a 2x10 rafter for the exact same roof, then the ridge board, of course, will be higher. Exact same slope, same angle, but we will have a higher ridge board. So the rafter stand is a very important dimension because we will need that in order to calculate or in order to set the ridge board at the correct height. In order to set the top of the ridge board, then we need to look at our diagram, look at our rafter. Actually, we need to actually determine whether the rafter is going to be a 2x6 or a 2x8, and then from that piece of lumber, we're going to be able to figure out or to calculate out the rafter stand. So once we have the rafter stand, if our ridge board was cut so that it was actually coming to a peak, the same angle as the slope of the roof, then what we would have is the top of that peak would actually be the total rise plus the rafter stand. In most cases, that's not done. People generally just leave the rafter board square cut at the top. So in that case, we need to drop it just a little bit so that the imaginary peak line is still in line with the top of the rafters. So in the little inset picture on the left-hand side, you can see in this particular case that this is a 612 roof, and the amount X that we have on the left-hand side in the ellipse is going to be the amount by which we're actually going to drop the top of a flat rafter board. So when the rafter board is cut on a flat or left on a flat, then we will have to drop it just a little bit. So to do that calculation, again, we use similar triangles. X over 3/4 is 6 over 12. And the math on that, we get that X is equal to 3 over 8. If we were working in metric, a ridge board thickness, 1.5 is actually 38 millimeters. Half of that would be 19 millimeters. So it would be X over 19 is equal to 6 over 12, which is the same as 1 over 2. And from that, we would get that X equals 9.5 millimeters. So 3/8 of an inch, 9.5 millimeters, same number, same measure. Now, so then when we go to set our ridge board, the actual rise to the top of the ridge board then will be the total rise plus the rafter stand plus, or sorry, not plus, minus the ridge drop. So we have total rise plus rafter stand minus the ridge drop. That would be 5 feet plus 4.5 inches minus the 3/8 inches, and that will give us 5 foot 4 1/8. When we're dealing in the imperial system, the amount by which you drop the ridge is consistently equal to, always equal to, the unit rise from the slope over 16. So let's say you're dealing with a 712 roof, then the amount by which you drop the ridge will be 7 over 16. In this case, it was a 612 roof, so it was 6 over 16, which is 3/8. If we're dealing with a 1212 roof, which is 45 degrees, then the amount by which we would be 12 over 16, which is 3/4 of an inch. Here we have a schematic of a roof, again a section cut right through it. This time all of our numbers are in metric, but we have the same principles at work. In a metric roof, the unit roof triangle is based on the number 250 millimeters, as opposed to imperial where it's based on 12 inches. So we have the same sort of a ratio going. And in this case, we're given that the roof slope is 150 to 250. We're given that the total span is 5,000 millimeters. The total run then being half of that, which is 2,500 millimeters. So simply by inspection, looking at the relationship between the big triangle and the small triangle, we'll see that the big triangle is 10 times bigger than the small triangle, which will then mean that our roof rise, or total rise, would be 10 times 150, which would give us 1,500 for the total rise. Now, using Pythagoras' theorem to that, or applying it to that, we get the line length of the common rafter is the square root of the total run squared plus the total squared, which would be the square root of 2,500 squared plus 1,500 squared, which is 2,915 millimeters. And remember, when you enter this into your calculator, that you include the brackets. Okay, it's very important you have the brackets. If you don't have that, you'll get the wrong answer. So what you need to enter is the square root button, open brackets, 2,500, the x squared button, plus 1,500 squared button again, and then close your brackets before you hit the equal sign. Hit the equal sign and you'd get 2,915. The other way to do this is recognizing that the big triangle is 10 times bigger than the small triangle, is we simply take the hypotenuse of the small triangle, which is 291.5, multiplied by 10, and we get 2915. Now, why this is important is because that number, 291.5, is actually found stamped on the framing square. And in the same way, when we do an imperial roof, the hypotenuse, if for instance it's a 712 roof, the hypotenuse of 13.89 is stamped on the framing square. So we're actually able to use our framing square to get the numbers and get the lengths. We're actually doing the same thing when we set our stair gauges on the framing square. We're actually sliding along the top of the rafter, and you can see in the diagram there are 10 triangles, which means there are 10 hypotenuses, which would give us our total length of our rafter. It's important to do the calculation though, because that will avoid any error that we might accumulate by sliding our framing square. If our error is only half a millimeter, we slide it 10 times, we have an accumulative error of 5 millimeters, which adds up. So it's important then that we do our work carefully, and this is the way we would do our calculation. Notice the projection in this diagram is to the outside of the fascia, and it's 305 millimeters. So when we go to cut a rafter in this case, we have to make sure then we adjust for the 1.5 inch thickness of the fascia board. This is the first part of your assignment. What I've done here is given you a diagram. I've worked with all the numbers for you, and then I'm going to give you some more for you to work on your own. So here we have the common rafter. We're going to try to figure out, we're going to try to label it, of course, and we have the names, the locations of all the cuts, and the calculations of the length. Our focus is mainly going to be on the math. We have a building that has a span of 20 feet, so if the building is 20-foot span, then the run is half of that, which is 10 feet. The slope is given to us as the unit rise over the unit run, which is 712. Remember, it's always over 12. Now here I've introduced something else called pitch. Now many people mix those two numbers up and use them interchangeably. They're not the same. Pitch is an old term, and what pitch meant was the unit rise over the unit span. So not rise over run, but rise over span. And just as the unit run is 12 inches, the unit span is twice that, which is 24 inches. And so in this case, for a 712 roof, or a roof with a 712 slope, it will actually have a 724 pitch. Now this number is always in lowest terms. In the case 7 over 24, we can't get any simpler than that. But let's say, for instance, our slope was 612. It would always stay and be called 612 slope. But when it came to the pitch would be 6 over 24, and that would get reduced to its lowest terms, which is a quarter. So a 612 slope roof would be called a quarter pitch roof. Slightly different. Generally speaking, pitch is something that is not used very much anymore. The framing square everybody uses, and that's based on slope. So you will have 712 on the framing square, 812, 912, 1012, no mention of pitch. So keep that as just as a bit of history. Now going back to the total rise in this case, and again, because we can inspect this roof and just see that the big triangle with a run of 10 feet is 10 times bigger than the small triangle, which has a run of 12 inches or 1 foot. So 10 feet, 1 foot, 10 times bigger. So to get our total rise, we simply take the unit rise, which is the vertical part of the triangle, 7 inches, multiply by 10. We get 70 inches or 5 foot 10. To get the unit common rafter, we would do Pythagoras on the little triangle. So the little triangle is 7 and 12, so the square root of 7 squared plus 12 squared would be 13.89. Now that number we can also find on the framing square, so we'll get to that in the next lesson. To find the total length then of the common rafter, we have two choices. The simple one, we take the 13.89, multiply it by 10, because the big triangle is 10 times bigger than the small triangle. That gives us 138.9, or 11 foot 6 and 7/8. Or we could do Pythagoras again to the big triangle, because now we know the base, we know the run, and we know the rise. So the line length of the common rafter would be the square root of the run squared plus the rise squared, which would be the square root of, I did this in inches, so 120 inches squared plus 70 inches squared which would give us 138.9 inches, which is the same answer of 11 foot 6 and 7/8. So I'm going to give you an assignment based on the same diagram. I'm going to change the numbers and the slope up a bit, and I want you to work through it just to get the practice of calculating the lengths of the rafters. Our next lesson is going to be now how do we actually cut the rafter? How do we transfer these numbers to the wood itself?